Now that you've learned about lists and loops, we're going to bring these concepts together and talk about algorithms in terms of both of these concepts. These two ideas, when you bring them together, it's kind of like the yin and the yang of computation. We can start to write algorithms for very large problems, but we need to learn how to break those problems down and think about them in a very step-by-step basis. So we're going to begin with a simple problem in terms of English. How would we sum four numbers such as 1, 3, 5, and 7? Right? Well, if you're telling a human, your friend, like, hey, what's the sum of 1, 3, 5, and 7? They can pretty quickly figure out, all right, well, 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16. Done, right? So 16 is the answer. Why do we need to think about this any more deeply than we just did? Well, when we're trying to express an algorithm, we need to think of it in terms of what the computer is able to carry out in its representations of a given problem. As humans, we can deal with the ambiguity of like high-level concepts and fill in some of the blanks on our own. But when it comes to computation, if you're writing an algorithm, you're going to need to be very precise and concrete in your steps. So how might we be a little bit more concrete here? Well, besides just saying add all the numbers up, we could imagine, add 1 to 3, then 5 to the total, then 7 to the total. Right? And okay, well, we've been a little bit more specific here, but this is almost too specific, right? What happens when I change one of these numbers to another 5? Well, what we just wrote, these instructions that we just wrote are now wrong, right? So we've become more concrete and specific, but we have also unintentionally fit the problem to too specific of a solution, right? Or too specific of a description of how to solve this. So our inputs shouldn't be specifically part of our algorithm, at their value level, right? So we shouldn't, when we think about how to describe an algorithm, we want to think a little bit more broadly, but still in a very precise way. So let's get some practice with that. And what we're going to do next is think about, well, we started from adding 1 and 3 together, but is that really the first step when you're trying to be able to add lists of arbitrary lengths? Well, let's imagine, okay, we've just been talking about summing 1, 3, 5, and 7 as our list. And let's imagine this is in Python syntax, so this is a list literal here. Okay, that's fine. Well, what would be our first step if we were summing, a list with just 1 in it? Well, we wouldn't add 1 to the next number because there is no next number. So we're going to need to be a little bit more careful than that. And we're probably going to want to start from 0, right? Can you think of another reason why we might want to start from 0? What's the sum of a list that has no elements in it? Well, typically we would assume that that's 0. It has no value to it. There's 0 elements in it. So when you add 0 elements up, you get nothing, right? Nothing plus nothing is nothing. So let's keep track in terms of some total starting from 0. So we're going to have some total, and it's initially 0. Now, previously we were thinking in terms of, okay, we'll add 1 and 3. How can we be a little bit more generic than that and think about, instead of 1 and 3, well, what if our list was, 2, 4, 6, 8? Right? How could we think of the first two numbers, or the very first number, more generically? Well, we want to think about adding items of a list as their particular place in the list, right? So maybe the first item in the list. What's the first item in our lists? In either of these cases, it's not necessarily the value 1 or 2. More generically, it's the item at index 0, right? So remember, every list, its items are indexed 0, 1, 2, 3, and so on, right? So if we imagine that these are I'm going to just call this list X's. Imagine this is the list X's, and our total is 0, right? So X is at index 0 would refer to the value 1 if X's was this list, but if X's was this other list, it would refer to the value 2. So by thinking in terms of, a generic, our list name is, say, X's, And our index is something that we now need to keep track of. So index is going to refer to which item in the list we're trying to access and add up. So x's, let's think of this as index, and I'll use the letter I to keep track of an index. Index is 0. Right, now I'm gonna, for now, just remove this other example here, and we'll come back and talk about other examples in just a moment. Okay. All right. So how can we, again, still using English, but in terms of these two concepts, we now have an index and we have a total. How can we think of our steps a little bit more concretely? Well, we can start with total 0 and index 0, right? So that's step 1. What's step 2? Well, before we go and add anything up, we need to know whether or not we're dealing with an empty list, right? Or whether or not the current index is still valid. Right now, the index is 0. If we had an empty list, this would no longer be valid. So we want to just be sure, while the index is valid, but this idea of valid isn't very specific. It isn't very concrete. So what would it mean for I to be invalid? Well, if we're starting from 0, we want to be sure that it's, I is less than the length of the list, right? So if the length of a list, in this case, is 0 and I is 0, then it's not valid. If the length of a list is 4 and I is 0, 1, 2, or 3, then it would be valid. So any of those numbers are valid indices. But as soon as our index becomes 4, it would no longer be valid. So while I is valid, maybe we be more specific here. And what we mean by that, actually, instead of crossing this out, why don't I just circle it and say, I less than the length of x's, right? So I is less than the length of x's, which is what we mean by valid. And notice we're waving our hands a bit, just trying to feel out this problem and become more specific as we move through it. Okay, so if we know that we have a valid index, that means that what we want to do is, step 3 is take x's index I and add it to total, right? Updating total, and that's important. We're continuously updating the total each time we add a new item to it. Okay, so this will work for the very first item, and this would be a good enough algorithm if we had just what's the sum of the list with only 3 in it. Well, okay, I is 0. 0 is less than the length of this. The length of this is 1. So this is a valid index. We take x's index 0, which would be 3, and add it to total. So total would then be 3, and then we're done, and that's fine. But this is no longer valid as soon as we have a second index, right? So how will we make this algorithm handle the next index? And this is where the beauty of being able to index or subscript your lists and the ability to loop in an algorithm or a program really become powerful. So what are we going to do? Well, let's update to I to be the next index. So update I to be the next index. And what do we mean by the next index? Well, if we're trying to be a little bit more specific about this, this is the same as, +1, right? So if I is initially 0, the next index is 1, the next index is 2. So we're going to increment I by 1. So that English can be a little bit more specific. And after we've done that, what do we do? Well, this is where the looping comes into play. We're going to go to step 2, right? So this is the end of our loop, and we're going to go back to step 2, and we're going to ask again, okay, well, we just changed I. I is now 1. If we were thinking about this simple example, we would ask, is that still valid? So 1 is less than the length of this, which is 2. So, okay, that's still true. Then we're going to go to step 3, which is take the next item, I at index 1, add it to our total. Now total in this case would be 7, and continue on. And if we were to think about this in terms of, our original example with 4 elements in it, this same algorithm should hold, right? We should just be able to move on to the next index, take its value using the current, x is at index I. So index 1 would be 3, index 2 would be 5, index 3 would be 7. Each time we do that, we update our total to add this amount to it. And then we update our index to go on to the next index until we reach the point at which the index is no longer valid. So when step 2 becomes false, we need to do something else. So when I is valid, we're going to do we're going to go into step 3. Otherwise, we're going to, and this is going to be kind of sloppy here, but otherwise, if I is not valid, we're result is total, right? So whatever's left in our total variable after we've moved through this algorithm is going to be the sum, okay? So this is sort of some intuition behind how we are going to sum a list of numbers. Let's jump into actual VS Code and carry this out. Right, so I'm going to set up a file that will be named, let's call it sumalgo.py. Okay? And let's just add a description here that is examples of lists and loops, list and loop algorithm. Okay. Let's say we wanted to define a function that could carry out our summation. Right? So define sum algo. Right? So what was the input to our summation? Well, it was this idea of having a list of integers, say. And we're going to name that x's. Right? So xs is a common shorthand name for just an arbitrary list of call it numbers. And the result of this algorithm is an integer. Right? So for now, I'm going to make this what we call a skeleton of a function. And it's going to have all the components to make it valid, but it's not going to yet be a valid function. So let's add a doc string here. Summation of input list is returned. Right? Great. And this function isn't correct yet. So how do we go from having an incorrect, but it does return the correct type, right? So this return statement, if we were to call some algo from somewhere else in our program, it would return 0. That actually satisfies the return type of our function definition. So this is a valid function that's incorrect, and you'll commonly come across those, and that's usually your best starting point when you're trying to implement a function like this. Okay. So we've got x's, and let's go return back to our notes. So our notes were start with a total of 0 and I of 0. So what I like to do is take my steps that I've written out in English, sort of the overarching goal of some task I'm going to carry out in code, and reproduce those as comments first. So I'm going to add a comment here. So step 1 was initialize total and index I to 0, right? And before I even worry about implementing this as code, I might go ahead and jot down some of the other steps, right? So that was step 1. Step 2, while index I is valid, meaning I is less than length of our x's list, right? And I'm going to indent to say, okay, when 2 is true, right? Then what do we do? Well, we said we're going to take x's at index I and add to total, right? But that wasn't all we wanted to do when 2 is true. So the next thing we would do inside of this, what's going to become a loop, is we need to be sure that we move our index to the next index. So we started from index 0, the first item in our list, and now we need to move on to the next index. So increase I by 1, moving it to the next index. Okay. Now there was a case where 2 is false, right? When 2 is false, the result is stored in our total variable, right? This is sort of where we're keeping track of the accumulated result. At each time we sum a new number to our total, it's being stored in our total variable, and ultimately that's going to be our result. Okay, Now that we have these steps in English, let's try turning them into code. Okay, initialize total and index I to 0. So total is going to be an integer variable and initially 0. I is also going to be an integer variable and also initially 0. Okay. While I is valid, meaning I is less than the length of x's. Okay, so while I is less than the length of x's. Okay. Now, that intuition is sort of nuanced, but we previously talked about if you want a loop to run a specific number of times and you start your counter variable, which is I, or index here, at 0, then we want a loop while that counter variable is less than the total number of iterations we want to run, because we're counting from 0. There's this off by 1 factor where we have to shift everything by 1. And because our length, the length of a list, if we have one element in our list, the length is 1 and the first index is 0. And so that's what's going on here. Now, the next thing we want to do is actually be sure that the next two steps are contained inside of the body of this while loop. So one of the things that we haven't discussed yet is, if you want to indent a number of lines of code at the same time, how would you do that? Well, one way is, you select the beginning of each line and you tab them in individually. But this is such a common operation when you're programming that what you'll tend to want to do is select all of the lines that you care about. So I'm going to use my mouse to select both of these lines, and you don't have to select the whole lines as long as you have parts of the line selected. And then if you press tab, it's going to indent every line you have selected by 1. And then if you hold down your shift button and press tab again, the shift will sort of do the same thing in the opposite direction. I like to say unindent, but I don't think that's actually a real word. Okay. So you can very quickly, indent, unindent. I'm going to indent my directions here and say, okay, well, what do we want to do here? We want to take x's and add it to the total. That means we're trying to reassign total. So this is one of those cases where when you're turning English into code, you have to be comfortable with, well, what are the statements that are valid programming statements? So we know a statement like total is assigned total plus x's of index I. But we just learned that we can actually write this with a little bit of shorthand using our relative reassignment operator. So this is the same as saying total is incremented or increased by the value stored of x's index I. Again, the first time this loop runs, I is going to be 0. So we're saying take the current value of the first item in our list and add it to our total. But as this is written, we currently have an infinite loop, right? We're not changing anything nothing in this loop is changing anything about this condition. We need this condition to ultimately become false at some point in order for this not to be an infinite loop. So more logically, what we want to do is be sure that we move our index to the next index. We started from index 0. We added the first element of our list to our total. Now we want to move to the next index. So how do we do that? Well, we could say I is assigned I plus 1, or as we just learned, I plus equal 1 increases I by 1. Great. Notice that this means each time this loop iterates, we take the value stored at the current index, we add it to our total, and then we move to the next index. We take that index, we add it, whatever item is stored in that index, to our total. We increment our index, and we keep following out this procedure or this process until this is no longer true, right? So once the index we're looking at is no longer a valid index, meaning, there just isn't an item stored there in our list. We've got an index that's beyond the end of our list. That's when we're done with this loop and we're ready to return our total. So our result is stored in our total variable. So that's probably what this function should return total. Great. All right. Well, now we've written a generic algorithm. Let's actually see if this works. Let's try testing this out. One of the things I want to show you when you're writing a program or a function like this, and we're abstracting away this process, this function is an abstraction of the summation algorithm. Once we have this function, we don't have to think about all these details in a very low level like we just did. We can think, hey, I want to add up some numbers, so I'm going to use my sum function. So how can we actually use this in a VS Code REPL? Let me make this a little bit smaller so it all fits. What I'm going to do is I'm going to start up a REPL. And now I'm going to import this function. All right, so this is something new in our course. I'm going to say from lessons.sumAlgo import sumAlgo. Right, so this is a little bit funny because I named the file here sumalgo.py, lessons, and then the module name is sumalgo.py. And then we also named our function sumalgo.py. So that's why we're saying, this is saying from the package lessons, the module sumalgo, which is this whole file, we're going to import this function. If we had more than one function here, functions had different names, we would have said import, function foo if there was a function named foo. Okay. So I've imported the sum, and now let's try, seeing if it works. So sumalgo, and then we're going to give it, let's say, a list literal of the empty list. Let's start with something simple. Boom, the sum of the empty list is 0. That's great. Well, what about the initial item or the initial list we started with, 1, 3, 5, and 7? And we calculated that as humans to be 16. And wow, it looks like our implementation here is letting us know we're correct. We could also try sumalgo of, say, 2, 4, 6, and 8, just to convince ourselves this is a generic algorithm that works for different numbers. And boom, what do you know? We've got 20. 2 plus 4 is 6. 6 plus 6 is 12. 12 plus 8 is 20. Great. Sumalgo of, let's say, one item in our list, 110. 110. All right, so it seems like we've got the ability to have lists of arbitrary lengths as our inputs here. And our sum algorithm works, even though nothing changed about it, right? We didn't change any code. Our algorithm is still the exact same sequence of steps, but the way that we specified it in terms of a list and having each item in that list indexed, and a loop which uses an index to move one by one through each item in our list, we're able to write this algorithm which abstracts these details away from us. I should also mention that we don't have to use a list literal here. We could set up a list of, say, odds, right? Which is a list of integers. And odds is going to be values such as 1, 3, 5, 7. Now let's make the computer work a little bit harder here. We'll add 9 to our list. And now we could say sum of odds is an integer variable, and we could store in that integer variable the result of calling sumalgo with the odds input list, right? So because this is a function, we can use as an argument that corresponds to the parameter x's any list that's of the correct type, a list of integers, right? And it's going to return to us something of type integer, that the sum, and we're going to take that sum and store it in this variable, right? So that statement has evaluated, and so now if we were to print sum of odds, boom, 25, right? Now I want to mention that when you're working in the REPL, you don't have to print your results, right? You can just access an expression in whatever, if you write just a plain old expression in your REPL, what REPL is short for is read your input, evaluate it, and then if it's an expression, it's going to automatically print it for you. That's the P in REPL, and then the L is loop, and it's literally a loop, just like we're writing here, that brings you back up to the top, and it reads your next line of code, it evaluates it, it prints the result if it's an expression. Now that's different from, we had some statements here, like, the statement here, sum of odds, is an integer that is assigned the result of the sumalgo function being applied to the odds argument. That's a statement. And because that's a statement, nothing gets printed, right? Only expressions, when you're working in when you're working in the REPL, will automatically get printed. This is different from when you're working in a stored program and you have to print something yourself, right? So just as one last example of that, if we wanted to add an example of calling this function to our program here, I'm not going to go to the trouble of making a main function, but just so you have some notes and you can come back to this file and understand how it's called, let's try setting up a variable such as odds. That is a list of integers, and that is assigned 1, 3, 5, 7. And then we could do odds sum, which is an integer. That is the result of calling the sumalgo function with the odds list. And then we can just print odds sum, right? And we'll just make a note of this example usage of the sumalgo function. All right. And now if I were to run this program, Python M sum lessons.sum algo. Boom, 16. All right. So what we've seen in this video is the process of trying to describe an algorithm in English terms and in broad terms, and then think about, well, how can we bring this description a little bit closer and a little bit closer to a representation that we can write ourselves in a programming language such as Python. And this process of, we'll start with some comments that we think of sort of as pseudocode, like it's not really code, the computer has no idea what we're talking about, but we're thinking step by step in a way that we can then translate into Python instructions, is a very common strategy for taking on new problems when you're trying to program and solve a new type of algorithm. And I do this all the time, even today. And what we've done, which is really neat, is we actually have our first example of a process abstraction. This is a process, right? This idea of how do we take a list and from that list sum all of its elements and then return that result. That's a process that we had to think pretty deeply about in order to write this algorithm. But once we've written this function, sum algo, that's an example of process abstraction. Now we can just use this function anywhere we want to carry out this task, and we can think about it a little bit more like we would think about it among ourselves as humans, right? What do you want to, how do you add up a bunch of numbers? You add them all up, or once you've written this function, you just call the sum algo function and you don't worry about all those specific steps. Now I should mention that the sum function, and why we didn't name this just sum, is there's a function named sum built into the Python language, and it's a built-in function. It's available to you in every Python program, and it works in a very similar way. The reason why we in a computer science class will be looking at how are these algorithms actually implemented under the hood is because once you start needing to take on tasks that are beyond the scope of what's built into a language, you kind of need to have some comfort thinking in these ways. And it's helpful to know how it is that others have implemented the functions that you're using and they wrote for you and on your behalf. Great work in moving through this. In the next video, we'll look at how we would trace an algorithm like this and how lists are stored in memory, which is a little bit different from how our numbers and our Booleans are stored in memory. So great work, and I'll see you in the next video.